Hi, I'm Stephen Tran, and I'm going to be explaining the catalyzed decomposition of hydrogen peroxide, otherwise known as H2O2. Now, normally in this reaction, you have two molecules of H2O2, and over time they decompose to two molecules of H2O and one molecule of O2. H2O being obviously water, and O2 being oxygen gas. Normally, however, this reaction takes a very long time to proceed. So what I'm going to be explaining and showing today is how the catalyzed decomposition would happen. I've shown in other videos how catalysts work, and I'm going to give you a tangible example of one working today. First, I'm going to show you on the board how it works, and then we're going to get into the fun chemistry. I'll show you outside the actual reaction. So, like I said, normally this is the reaction that proceeds, and it proceeds very slowly. Now, the catalyzed decomposition reaction, which normally would involve Ki, looks a little bit like this. It happens in two steps, and it involves an iodine anion catalyzing the reaction. Now, this iodine anion can be introduced to the system through potassium iodine, which it's a salt, and when put in water, it'll actually break apart into K plus and I negative cations and anions. So what's actually happening in this reaction is you have one molecule rather, of I minus, and it reacts with this H2O right here. And what it actually does is it pulls off one of these oxygens. So you'll see if you look to the right, I minus is now bonded to an O, and this H2O is the result of you pulling off an oxygen from this molecule right here. Now, so that's one of your products right there. That's one of the H2O molecules. Now in the next step, you have another molecule of H2O2, and it's reacting with this intermediate right here that you just formed. And what happens is this O will actually pull off one of this molecule's O's, and you'll be left with H2O, so it's pretty much this minus an O, and you'll also be left with O2 now, this oxygen plus one of these oxygens. So if you look at the overall reaction, you have one H2O here, one H2O here, and O2 here, which is exactly this reaction right here. 2 H2O, 1, 2, goes to 2 H2, 1, 2, and one molecule of O2. Okay. Now, this is actually an example of an intermediary catalysis. This I is, it reacts here and forms this intermediary, OI, and this intermediary is actually reacted with another molecule of H2O, H2O2, to form these final products. However, you'll notice, and this is kind of the trademark of catalyzed reactions, that whatever the catalyst is not consumed in the reaction. So you'll see you start with I over here, and you end with it. It's never actually used up in the reaction. So this I can actually participate in this whole process again, and that's actually what happens. So when I will be used up here, it'll be one of the products here, and it'll just keep going through this whole process again and again and again until there's no more H2O2 to react. That's about it. So now we'll, in a couple minutes, we'll be getting to the fun part of the actual reaction. So, I've just realized we don't have any potassium iodide to use for our reaction. So, unfortunately, I'm not going to be able to show you the potassium iodide catalyzed decomposition of H2O2. Luckily, however, I have a little something called yeast. Now, yeast and potassium iodide are two very different things. This is just a simple chemical compound, while yeast is an actual living organism that is often put into baked goods to help them rise. Luckily, however, there are certain enzymes in yeast that can catalyze reactions. And Brianna has actually talked about how enzymes can make reactions proceed faster and lower the activation energy and what have you. So the good news is that we'll actually get to see an enzyme catalyzed reaction. So what Brianna has pretty much been talking about, while also understanding the chemistry of it, because the reaction essentially proceeds in much the same way. The enzymes, whatever they may be in yeast, they're a little too complicated to explain here, but the enzymes that are in yeast will react in much the same way that I negative does, I minus. So they'll catalyze the reaction to here, and then catalyze the reaction to here. So essentially, you will go from these starting molecules, two molecules of H2O2, to our products of water and oxygen gas. They just won't be in this exact way, but essentially it does the same thing. So yeah, we're going to be using yeast. It'll accomplish the same thing, and let's get out there. Okay, so we're about to do our reaction. we have our hydrogen peroxide, which is actually 40% hydrogen peroxide, which is a lot stronger than your normal drugstore brand. We've got our yeast, which is our catalyst, and we've got some dye and some dish soap. Those will help make the reaction a lot more visible and easy to see. So we're going to take our hydrogen peroxide. Oh, this is going okay. 2. Add a little bit more in so we get a good reaction. Okay. So that should be good enough. Oop, let's pull a little bit. Alright. So the next thing we're going to do is we're going to mix in a little bit of dye to add some color to our reaction. And a little bit of dish soap. That's going to help the reaction be a little bit more visible. Okay. Now we're going to prepare our yeast catalyst next after I mix this up a little bit. Okay. Should be good. So let me open this up. Put the yeast in. You actually hear the reaction taking place a little bit. This is what's actually happening. The yeast is catalyzing the hydrogen peroxide that leaked out of the bottle. So that's what it normally would look like, with gas evolving and a little bit of heat evolving too. But our experiment's going to be a little bit more exciting than just some bubbles. Alright, that should be enough. You know, we'll add one more just for fun. Pour in some water, then mix up a little bit. Because if you just put the solid in, you're not going to get as good a reaction as if you were to dissolve it in some kind of, solution like water. Mix it up real good. Okay, we've got our catalyst, so get ready. Stand back. So you can see it's a pretty exciting reaction. I didn't even have enough time to get all the catalyst in there, but what's actually happening is the O2 gas is evolving, but it's getting trapped by all the soap bubbles. So that's why it takes this form, which actually kind of looks like toothpaste or something like that. And it's a little hot, but you can actually pick it up, and it's pretty much foam, soapy foam. So what you might clean your dishes with or something like that. So that's our reaction, and I hope you enjoyed it.